Okay, we're going to talk about the central limit theorem and the sample mean. And let me get a better color for this. All right. Here. Okay. Going to use the sample mean. Okay, so let's look at what we have here. This first column, okay, is data, and it goes way down. The column goes way off the computer screen and way further off than this. It's just a lot of data. Okay, what I've done with each of these columns, okay, is I've gone in and I have sampled, okay, data from this column over here. Just taken a random sample. Here there are 30 numbers here. I have just taken these randomly from this right here, and I've done it for each of these, and I've just chosen 10. I've done a lot more than that. Okay, and okay, so taking those samples, and then each of those samples, okay, I've taken an average. So this number right here represents the average of that column. Okay, this sample right here is the average of this column, and so forth. Each of these numbers here, each and every one of them represents the average of a column. Okay, and I've taken the means and the standard deviation and the standard error of the mean, which we will talk more about later. Okay, now I took that data, okay, and by which I mean this right here. So the means of all of those columns. Okay, so these are values of our random variable that's called the sample mean. Okay, and so here I took it and I graphed it, and okay, guess what? It looks like a bell curve. Okay, it looks normally distributed because it is normally distributed. Okay. Okay, so the sample mean. Okay, so we let x be a random variable on some population. Okay, you got a population out there. You've got a random variable that assigns numbers to it. Okay, and then we decide to take a sample size from that. Okay, the sample mean, x bar, is the random variable that assigns to each sample its mean. Okay, so each of these populations is going to have just a large number of samples of size n. You just assign the mean to each of those samples, and the random variable that does that is the sample mean. And so notice we have a connection of the notation here. Your original notation is x. The sample mean from that's going to be x bar, and somewhere you have to have set a sample size that you're going to take. Okay, so right here, okay, go back to my original data. These values, you know, are x. Okay, we look, and here, okay, these are the samples that I'm taking from x, and each of these particular values here is a value, right, from x bar. Okay, so you have the samples, right? So this sample is in fact a member of your population, right? And to it, that member of the population, you assign a particular value. Okay, and so the means of the samples are the values of x bar. Okay. The standard error of the mean is the standard deviation of the sample mean. So you go through all possible samples, take all of their possible means, and then average that. So you're averaging averages. The standard deviation of that, okay, is your standard error of the mean. Okay. So what is the value? We can actually calculate it. Okay, we're not going to do the math for you here, but okay, if you have a population of size capital N and you're taking samples of size little n, then the standard error of the mean is, okay, sigma sub x over the square root of n times this fiddle factor. Okay, and for small n. Okay, now what happens? We have this different formula for large n. What happens when n is large? Okay, so imagine n is a number like 30. Okay, and so you take a 1,000, or actually better, 1 billion minus 30 divided by 1 billion minus 1. Well, that is almost 1, and you take the square root of it and it's even closer to 1. And so for large n, we say, hey, you know, we're just doing statistics anyway, let's just make life simple and round it off to that. Okay, now here we come to the slide, which is the title of this presentation, the central limit theorem. And what it says is, for a large population with a sample of size n bigger than 30, that this standard, the sample mean is normally distributed. It has a mean equal to the mean of your original random variable, and it has a standard deviation equal to sigma sub x bar, but remember, sigma sub x bar is sigma sub x over the square root of n. Okay. All right. So let's see how this plays out. A bag filling machine fills bags of sugar with an average of 5.1 pounds. Remember, if you want, you've got a 5-pound bag of sugar. If you want each bag to contain at least 5 pounds, you're going to have to, on the average, have a little more than 5. Say we have a standard deviation of 1 pound. Okay, we have 100 bags are removed from the line and weighed. What is the probability that the total weight is less than 500 pounds? So let's look at this. Okay, so we take this sample of 100 bags from the line. What is the probability that the weight is less than 500? Well, the central limit theorem gives us information about the sample mean, so we take this and we divide both sides by 100 so that we can get the sample mean on this side. So we have this, we can rephrase this: what is the probability that the sample mean is less than 5? Well, our sample mean is normally distributed with a mean equal to 5.1 and a standard deviation equal to 0.1 divided by the square root of 100, right? Because we have a n equal to 100. We do the math on this, and that comes out to 0.01. Okay, so the probability z is less than 5 is, well, we take the z-score of both sides, and so this is the probability z is less than -10, and that just doesn't happen. And it's just, remember, your normal curve is here, right? And when you get past like -3, there is nothing under it. So when you get past -10, for sure nothing is under it. Example 2. A bean filler is putting beans into sacks, and the sacks are supposed to contain 10 pounds of beans. However, it is discovered that on average each sack contains 10.5 pounds of beans with a standard deviation of 0.07 pounds. If a sample of 49 sacks is taken, what is the probability that the average weight will be between 10.2 and 10.5 pounds? Okay, so our standard error of the mean is the standard deviation of the original random variable divided by the square root of the sample size, so it's 0.7 divided by 7. Okay, so it's 0.01. And so the sample mean, okay, is normally distributed with a mean 10.05 and a standard deviation of 0.01. Okay, what's the probability that x bar then is between 10.02 and 10.5? Well, you take the z-score of everything in sight, okay, and you do the math on it, and this is the probability that c is between -3 and 0, and this is just a table lookup, and so our table lookup is 0.4987, almost 50%. Okay, estimators. Estimators are statistics that we use to estimate parameters when the true value is not known. Okay, so this sample mean is an estimator for the mean. The sample standard deviation is an estimator for the standard deviation. Okay, so let's see. A health inspector samples 100 cans of Madame Filtheria's homestyle chili and discovers that the cans, on the average, contain 4.6 rodent parts with a sample standard deviation of 2.2 parts. What is the probability that they can contain more than, that a can contains more than 5 rodent parts? Okay, so taking a sample of size 100, okay, again, x bar is 4.6, the sample standard deviation is 2.2. Okay, well, here's the thing, we don't know this sigma sub x bar, and in practice we never will, so we use this estimator 2.2, just plop it right into place there. And so that our standard error of the mean is approximately 2.2 divided by the square root of the sample size, which is 0.22, and so our sample mean is, okay, normally distributed with a mean of 4.6 and a standard deviation of 2.2, and so the probability that x bar is greater than 5, well, we take the z-score of everything, you know, so we can do the calculation. This gives us the probability that z is greater than 1.82. This is a tail, and so it's a thin tail, as a matter of fact, so we get the 0.5 minus 0.4656, and so this happens, you know, 3.44% of the time.